Dear students, now we are going to see the subject linear integrated circuits. Subject code is EC3451 and that the topic is voltage references. On completion of this voltage reference, students will be able to summarize the different types of voltage references. The circuit voltage reference circuit that is primarily designed for providing a constant voltage independent of changes in temperature is called voltage reference. The most important characteristics of voltage reference is the temperature coefficient of output reference voltage TCR, and it is expressed as TCR equal to dVR by dt. The desirable properties of voltage reference are: the reference voltage must be independent of any temperature change. Reference voltage must have a good power supply rejection which is independent of supply voltage as possible, and the output voltage must be independent of loading output current as possible, or in other words, the circuit should have a low output impedance. Voltage reference circuit using temperature compensation. The circuit diagram is shown in figure. This in temperature compensation, two diodes are connected back to back. The design utilizes the close thermal coupling achievable among the monolithic component. This technique compensates the known thermal drift by introducing an opposing and compensating drift source of equal magnitude. A constant current I is supplied to the avalanche diode dB, and it provides a biasing voltage VB to the base of Q1. The temperature dependence of VBE drop across Q1 and thus across D1 and D2 result in respective temperature coefficients. Hence, the use of resistors R1 and R2 with the taping across them at point N compensate for temperature drift in base emitter loop of Q1. This results in generating a voltage reference VR with normally zero temperature coefficient. Voltage reference circuit using avalanche diode reference. A voltage reference can be implemented using the breakdown phenomena condition of a heavily doped PN junction. The Zener breakdown is the main mechanism for junctions, which breakdown is at voltage 5 volt or less. For integrated transistor, the base emitter breakdown voltage falls in the range of 6 to 8 volt. Therefore, the breakdown in junction of integrated transistor is primarily due to avalanche multiplication. The avalanche breakdown voltage VB of a transistor incurs a positive temperature coefficient, typically in the range of 2 millivolt per degree centigrade to 5 millivolt per degree centigrade. So that avalanche diode compensated voltage references shown in figure. The figure depicts the current reference circuit using avalanche diode reference. The base bias of our transistor Q1 is provided through resistor R1, and it also provides the DC current needed to bias DB, D1 and D2. That the voltage at base of Q1 is equal to the Zener voltage VB added to the two diode drops due to D1 and D2. The voltage across R2 is equal to the voltage at the base of Q1 less than the sum of base emitter voltage of Q1 and Q2. Hence, the voltage across R2 is approximately equal to voltage across dB, and that is equal to VB. Since Q2 and Q3 act as a current mirror circuit and I not equal to the current through R2, I not equal to VB by R2. The output current I naught has low temperature coefficient if the temperature coefficient of R2 is low, such as that produced by diffused resistor in IC fabrication. The zero temperature coefficient for output current can be achieved if diodes are added in series with R2 so that they can compensate for temperature variation of R2 and VB. The temperature compensated avalanche diode reference source circuit is shown in figure. The transistor Q4 and Q5 form an active load current mirror circuit. The base voltage of Q1 is the voltage VB across Zener dB. The VB is equal to VBE into N plus VBE across Q1 plus VBE across Q2 plus drop across R2. Here N is the number of diodes. VB equal to n plus 2 into VBE minus I naught into R2. Differentiating VB, I naught, R2 and VBE plus partially with respect to temperature T, we get dou V by dou T equal to n plus 2 into dou VBE by dou T plus R2 into dou I naught by dou T plus I naught into dou R2 by dou T. Dividing throughout the above equation by I naught R2. So 1 divided by I naught into dou I naught by dou T equal to 0 equal to 1 by R2 I naught dou VB by dou T minus n plus 2 into dou VBE by dou T minus 1 by R2 into dou R2 by dou T. Thank you.